The revelation of a new exoplanet has cosmologists energized that it could, for sure, be indications of something going on under the surface for a really long time. The fantasy of finding life past Earth has enamored mankind. On account of the James Webb Space Telescope, that fantasy could soon become reality. The telescope has, as of late, uncovered an interesting mystery in Proxima Centauri, the nearest star framework to us. In the midst of its planets, Proxima B stands apart with bizarre fake lights, leaving the researcher local area both astounded and captivated. Might this at some point be the hotly anticipated proof of canny life past our planetary group? How do researchers decide if these lights recommend the presence of wise life on Proxima B? Go along with us as we dive into how the James Webb Space Telescope distinguished SETI lights 7 trillion miles from Earth. People have continuously been strongly inquisitive about the mysteries of the universe. Through mechanical advancements, our intrinsic drive to investigate the Earth and sky proceeds unabated. Regardless of thousands of long stretches of human progress, Earth stays the just planet known to have life. This brings up the deep-rooted issue. Are we alone in the universe? Or are there civic establishments concealed among the stars, ready to be found? To track down replies, 2 American stargazers, Jill Tarter and Thomas Child, started the quest for extraterrestrial insight, SETI, project in 1984. This charitable undertaking intended to distinguish spaceborne radio transmissions, equipped for voyaging huge distances and possibly filling in as means for extraterrestrial correspondence. The project zeroed in on 42 radio telescopes in the Californian Fountain Mountains, known as the Allen Telescope Array. While researchers have filtered the skies for trustworthy signs over numerous years, to date, no persuading proof regarding signals from an outsider human advancement has been found. However, late reports from NASA recommend that the James Webb Space Telescope, JWST, may have distinguished counterfeit SETI lights from a close-by planet. Is there substance to this guarantee? How about we find out? The effective dispatch of the James Webb Space Telescope denotes a stupendous jump forward for mankind in understanding the universe. Situated around 1 million miles from Earth, this huge telescope is our entry to the earliest periods of the universe. Equipped with cutting-edge cameras and filters, JWST enables space experts to catch and dissect the many-sided colors surrounding heavenly objects, revealing insight into the arrangement of systems, stars, and planets. JWST's capacities reach out to segregating explicit frequencies of light, permitting specialists to assemble important data about the synthetic pieces and actual properties of heavenly bodies across huge distances. Beyond simple observation, JWST dives into the airs of exoplanets, looking for indications of something going on under the surface. Its unrivaled capacity to peer past the imperatives of existence has prompted momentous disclosures. For example, stargazers have uncovered beforehand obscure masses concealed inside huge worlds, testing prior thoughts about the universe's design. Only too many years prior, the realm past our solar system was generally unknown with no known planets. However, stargazers have since recognized north of 4,000 exoplanets circling far-off stars, a demonstration of human inventiveness and mechanical progression. As indicated by NASA, this number might address just a small part of the exoplanets dispersed all through the universe, indicating trillions really pausing to be found. In the persevering quest for extraterrestrial life, researchers are enthusiastically investigating the plausibility of distinguishing outsider environments past our ongoing comprehension. The James Webb Space Telescope, with its high-level capacities, is expected to assume a crucial part in this mission by meticulously mapping the orbital boundaries of possibly livable exoplanets within their stars' livable zones. JWST plans to uncover urgent proof in the quest for shrewd life past Earth. This denotes the start of another part in our excursion to unwind the secrets of the universe. As daylight goes through the air layers, its crumbled light conveying various frequencies is consumed by iotas and atoms. This absorption creates an unmistakable, unearthly design, similar to selective fingerprints, understandable through spectroscopic examination. It is estimated that when starlight arrives at a planet, JWST will identify it after entering the planet's environment. This ability positions JWST as urgent in uncovering the barometrical arrangement of far-off exoplanets, urgent for surveying their potential for Earth-bound life. Earth-sized planets with airs wealthy in oxygen, nitrogen, and carbon dioxide like Earth might hold conditions helpful for life, as we probably are aware. Alternately, the shortfall of anticipated components or the presence of strange mixtures could allude to elective types of life or even mechanical civic establishments. Intriguingly, the revelation of chlorofluorocarbon, CFCs, man-made compounds essentially utilized for refrigeration and modern purposes, might actually act as proof for extraterrestrial civic establishments. If JWST recognizes such artificial molecules in exoplanet atmospheres, it would strongly demonstrate extraterrestrial activity past our planetary group. This represents a fascinating endeavor for grandiose specialists, opening new entryways into the environmental arrangements of different universes and the chance of mysterious civic establishments past the Milky Way. For sure, disclosures about existence past our planet range a range of conceivable outcomes that challenge natural organic limitations. While we frequently envision life flourishing in calm environments like our own, reality might demonstrate undeniably more different and outrageous. For example, Extremophiles, a remarkable gathering of creatures principally made out of microbes, flourish in conditions typically considered ungracious. These strong creatures can get by and even flourish in conditions with temperatures up to 250 degrees Fahrenheit and pH levels under 3, highlighting the flexibility and versatility of life under outrageous circumstances. The huge aspects of the universe and its heap conditions urge us to grow our search for extraterrestrial life. While Earth-like planets circling stable, Sun-like stars offer promising valuable chances, we should likewise consider elective situations. Red small stars, M-dwarfs, despite being dimmer and cooler than our Sun, are more bountiful in the universe. They present special possibilities for exploring life in assorted conditions. The lengthy life expectancy of red diminutive people takes into consideration the slow development and advancement of life, possibly fostering complex life processes over the long haul. One ideal objective for JWST investigation is the TRAPPIST-1 planetary framework, found roughly 40 light-years away. This framework, with its faint red small star and 7 Earth-sized rough planets, incorporates 3 possibly livable planets with surfaces likely containing water. Another captivating applicant is Proxima Centauri, simply 4.25 light-years from the Sun, making it the nearest star to our own. In spite of its weak shine, Proxima Centauri's closeness offers tenable planets circling within its livable zone. Proxima B, found on August 24, 2016, is an enticing model. However, it circles extremely near its little red star, presenting it to extraordinary solar winds. Its position takes into consideration Earth-like temperatures where fluid water could possibly exist. However, Proxima B's close circle probably results in tidal locking, making one side of the equator be endlessly washed in extraordinary daylight while the other remains in ceaseless haziness. This current circumstance reflects the Moon's relationship with Earth in our nearby planet group. In spite of Proxima Centauri radiating just 18% of the Sun's mass, it discharges a weak gleam, essentially less light than anticipated for its size and vicinity to Proxima B, just 5% of the distance among Earth and the Sun. This challenges traditional assumptions, suggesting that Proxima B may not be the blazing fiery blaze one could expect for a planet so near its star. Despite these difficulties, its close circle and expected environmental misfortune due to solar winds offer fascinating potential outcomes. If it holds a defensive climate fit for capturing intensity, fluid water might possibly exist on its surface, making the way for the charming prospect of livability past Earth. However, getting just 65% of Earth's total solar energy, Proxima Centauri faces significant obstacles. Its plausible state of tidal locking makes outrageous temperature differentials between its scorching day and cold night. These cruel circumstances, compounded by its closeness to Proxima Centauri, subject Proxima B to extreme radiation, including X-rays and ultraviolet light, making it adverse to life as we know it. Moreover, Proxima B is assaulted by high-energy particles during heavenly eruptions. Unless the planet boasts a defensive attractive field like Earth's, these bombardments could strip away its climate, eradicating the circumstances vital for life to flourish. Reasonable demonstrating recommends that tidally locked planets like Proxima B may experience rapid atmosphere breakdown as volatile gases freeze out on the night side. Unlike Earth, where volcanic action renews the air, Proxima B lacks such mechanisms for air restoration. The secrets surrounding Proxima B extend beyond its surface conditions to its true capacity for hosting advanced civilizations. Right now, our comprehension gives little insight into Proxima B's volcanic activity or the strength of its attractive field. Anyway, the enticing probability of a climate-fuel hypothesis about the planet's true capacity for facilitating life. The presence of an environment on Proxima B would suggest the presence of oceans and raise the prospect of life. The mission to reveal indications of common development on Proxima B has escalated, driven by the speculation that such creatures might have formulated clever answers for surviving the planet's inimical circumstances. One interesting idea proposes sending huge sun-powered chargers across Proxima B's dayside. These boards would tackle the star's energy to enlighten and warm the perpetually dim and cold night side. Such an undertaking could change the distressing scene into tenable zones, capable of supporting life. The new disclosure of Proxima B has ignited a warmed race among space experts to determine whether it transits its star's face as seen from Earth. These developments would permit researchers to gauge the planet's size and mass, accordingly working out its thickness to affirm its rough organization and proposition bits of knowledge into the materials that comprise its stones. Additionally, starlight going through Proxima B's air during these travels gives hints about its environmental creation and livability. Regardless of the moves, the pursuit to unwind the secret of Proxima B stays a need driven by mankind's ravenous hunger for information and the chance of finding other life structures beyond our nearby planet group. One more element to consider is Proxima Centauri's tumultuous persona capable of huge eruptions. This expands the intricacy of examining Proxima B's livable potential. Stargazer David Kipping from Columbia College portrays the star as precarious, featuring the test presented by its variable warming examples. Dissimilar to rough planets that regularly absorb sunlight and produce infrared radiation, Proxima Centauri's case contrasts. Its infrared signature differs from that of its host star, introducing an interesting and open door for perception. The James Webb Space Telescope, JWST, acts the hero, able to do distinguishing these extraordinary infrared frequencies. Proxima's particular infrared heat signal is ready to disclose the secret mysteries of its climate. Outfitted with best-in-class infrared imaging capacities, the JWST is well ready to uncover Proxima B's climatic parts and proposition novel bits of knowledge into its likely tenability. Additionally, JWST's infrared awareness stretches out investigation to Proxima B's night side. In spite of the overwhelming challenge of distinguishing faint fake enlightenment against interminable darkness, the JWST's cutting-edge innovation empowers it to perceive even the slightest gleams of light. Proxima B's exceptional climate presents a dazzling connection between its surface elements and heavenly connections. The planet's dayside, if covered with sunlight-based chargers, could productively outfit the star's brilliant energy. All the while, its spectral edge could mirror approaching light beams as Proxima B finishes its circle around its host star. Its day-in and day-out sides experience indistinguishable cycles, portrayed by gentle daytime highs and cool night lows. Anyway, the greatness of temperature vacillations relies on the planet's structure. Without an environment, the distinction between Proxima B's constantly sides would be distinct. The day side would radiate heat like a dark body, while the night side would dive into cold haziness. By noticing the level of temperature variety, cosmologists can acquire significant experiences into Proxima's barometrical arrangement. With its unrivaled infrared imaging abilities, the JWST will examine the planet's warm discharges, giving priceless information about its air properties. Amazingly, the JWST's circle around Earth lines up with Proxima's orbital period, working with complete perceptions of the two its constantly sides within 11.2 Earth days. If Proxima B has a climate, the following stage is to examine its climatic science to see if it can support life. Certain gases, for example, oxygen, water vapor, or even methane if present, are phenomenal marks of tenable circumstances and the conceivable presence of life. However, this investigation requires carefully catching and analyzing light beams interacting with or going through Proxima's environment, an intrinsically testing attempt. While the James Webb Space Telescope gives tremendous open doors for describing planetary environments, its principal objective is diverse. The telescope is improved to dissect varieties in methane, carbon dioxide, and water vapor focuses. Although restricted in distinguishing fortified oxygen, a solid sign of life, JWST may still have motivations to look for different substances. This incorporates ozone, which could give data about the predominant essentialness in the planet's environment. Moreover, JWST's capacities are restricted to closer, possibly tenable universes. To lead a more exhaustive environmental examination, stargazers are turning to ground-based observatories like the Extremely Large Telescope, ELT, set to begin operations in 2028. The ELT is uniquely situated to dive further into the barometrical construction of far-off exoplanets, giving striking experiences into their tenability. As we anxiously anticipate the organization of future space telescopes, the James Webb Space Telescope, JWST, remains a pivotal device in our mission to comprehend far-off exoplanets. Notwithstanding its ongoing limitations, the JWST holds the possibility to give priceless experiences that will shape our way to deal with exoplanetary investigation for a really long time to come.